the two are not seeing eye to eye. So this is what motivated a broader, bigger, more general theory, which can be called sort of the theory of everything, which is what string theory is a candidate for. Now, unfortunately, string theory has its own issues, such as it is not testable. So even though it's been worked on, especially since the 60s, 1960s, and has come a long way, I would say, sure, a long way. I mean, the first sort of little what do you call steps into string theory happened as early as 1919 with that Kaluza-Klein stuff that we talked about, where Kaluza and Klein actually proposed one extra spatial dimension on top of general theory of relativity. General theory of relativity already set up the math in a way where you could actually propose extra dimensions if you really wanted to, because remember, general theory of relativity treats time and the three spatial dimensions in sort of an equal-ish footing, in a sort of space-time footing. The dimensions in general theory of relativity are not 3D, they're 4D, because it includes time, and space-time is what's being curved. Space-time, the fabric of space-time is what's being curved with by gravitation. So the way general theory does its math, remember we talked about, it's Riemannian geometry. It's not a Euclidean geometry. It's not the planar geometry that we're more familiar with, which is usually 3D or 2D and just involves the spatial dimensions that we all know and love: height, breadth, width, length. Did I say all of them? X, Y, and Z. Length, breadth, and height. Those are what we're more familiar with. And so if you had geometry that kind of just utilizes those three spatial dimensions, then we would be kind of comfortable. But there is geometry that involve more dimensions, extra dimensions, dimensions that we might not be familiar with and might not live in. And Einstein was kind of already doing that with his four space-time type of math for general relativity. And Kaluza and Klein proposed one extra dimension. They were pretty modest with their extra dimension and gave us some stuff back in 1919. And that sort of thing actually made a lot more progress in the form of superstring theory in the 1960s and onwards, okay? There was a time when pretty much it had to take a backseat because everybody's focus was more on quantum mechanics, okay? And even now, I feel like superstring theory takes a backseat, and quantum mechanics, particle physics, and associated developments actually get more funding, if I'm being honest. But these are the two sides that have been the quarreling two sides of physics.